more review of the second chapter of your summer assignment, which was focused on power polynomial and rational functions. There's also a little bit of logarithmic and exponential functions thrown in as well. We will be looking at this through the lens of mathematical modeling. And so the first question that comes up, well, what is a mathematical model? A mathematical model is a mathematical description, often by means of a function or an equation, of a real-world phenomenon such as the size of a population, the demand for a product, the speed of a falling object, the concentration of a product in a chemical reaction, the life expectancy of a person at birth, or the cost of emission reduction. The purpose of the model is to understand the phenomenon and more often make predictions about what's going to happen down the line. In order to really get into the thought process of modeling, we generally have a modeling process that we like to follow. So we start with a real-world problem, like if I wanted to predict population growth in 50 years from now, or if I wanted to try to determine the demand for a specific product. I would start with that problem, and I would start looking at the data and start noticing trends, and I would generate data plots and try to fit curves to models, and then what I would end up with is an appropriate mathematical model. Now, these generally will not be that pretty in terms of coefficients and things like that. You'll definitely be working with a lot of decimals. And then what we'll use is we'll take that data and we'll start plugging in numbers and values and start evaluating it and starting to draw mathematical conclusions. And from those data, the data that we collect from those conclusions, we're able to interpret them and then apply them back to the real-world concept, and we get what are called real-world predictions. And from those predictions, we start to develop new real-world problems, and it'll take us right back to the start, and we start the whole process all over again. Now, the thing that we have to understand is that a mathematical model is never a completely accurate representation of the physical situation. It's an idealization. A good model, and we use the word good very loosely, it simplifies reality enough to permit mathematical calculation and is accurate enough to provide a valuable and viable conclusion, but it's not always going to be 100% accurate. It's really important that you understand that there are limitations to any model that you create. In the end, we say that Mother Nature has the final say. So there are definitely outside limiting factors that will skew the results of any mathematical model that you can create. These are generally just created to get a good picture of what should be happening. It is not a set in stone rule of what is going to happen. There are many different types of functions that can be used to model relationships observed in the real world. And what we follow in this video, we're going to discuss the behavior of the graphs of these functions and give examples of specific situations that can actually be modeled by these functions. So let's start really simple. Linear models. When we say that y is a linear function of x, we mean that the graph of the function is a line, a straight line. And we can use everything that we know about straight lines and functions of straight lines in the creation of our linear model. So we can use the slope-intercept form of an equation to write a formula for the function as y equals f of x, which is equal to mx plus b. And you should remember that mx plus b is the slope-intercept form. We also have other forms, like, if you remember, we have point-slope form, which will probably be a little bit more useful when we talk about derivatives. But if you remember, that's y minus y1 equals m times x minus x1. And then we also have the standard form, which we probably won't use at all this year. But each one of these, and this would be x plus y equals c, where you take x plus y, you add, and you get some constant. We probably won't be using this one as much this year, if at all. Point slope will definitely be something we talk about later when we talk about derivatives and slopes of tangent lines. So, getting back to linear models, a characteristic feature of the linear model is that they grow at a constant rate. And you've probably heard this before. Linear models grow at a constant rate, or lines grow at a constant rate, or you'll hear the phrase the rate of change. So, for instance, if I give you an example, if you look in the graph of figure 2, we have a linear function, it's f of x equals 3x minus 2, and I give you the graph, and I also give you the table. Now, we generally dealt with in the past where if we go through the domain, we increase x values incrementally by integers. So if we started x equals 1, then the next value we would test would be x equals 2. And then we would test x equals 3. And actually, if we just sort of make a little table on the side here, if I know that x equals 1, I get 1.0. But if I get x equals 2, and I plug in, I'll get 3 times 2, which is 6, minus 2, which is going to be 4. And I can see that it increases by 3 to go from 1 to 4. What's really interesting about linear functions is that this constant rate actually happens as we get larger and also as we get smaller. So if you notice in the table, the change in x is actually very small. It's only by tenths, so it goes from 1.0 to 1.1. And if you notice, I go from 1.0 in my f of x value to 1.3, then to 1.6, to 1.9, to 2.2, to 2.5, and this rate is also going to be increasing at a constant rate. And this is increasing by 0.3 every single time. To sort of simplify the language, we can also say that whenever x increases by 0.1, the value of f of x increases by 0.3. So you can say that f of x increases 3 times as fast as x. So the slope of the graph of y equals 3x minus 2, namely 3, can be interpreted as the rate of change of the function y with respect to x. So we're saying that the rate of change of this function of y with respect to x is 3. It's increasing 3 times as fast, or the y values are increasing 3 times as fast as the x values. Let's try a model. As dry air moves upward, it expands and cools, and if the ground temperature is 20 degrees Celsius and the temperature at the height of 1 kilometer is 10 degrees Celsius, express the temperature T in degrees Celsius as a function of height in kilometers, assuming that a linear model is appropriate. So we're assuming that this is going to be a linear model, and there's actually a lot of information here that is not directly stated to you. For example, it says the ground temperature is 20 degrees Celsius. Now, what you might not realize is that actually gives you a variable value, or a value to start with. That's actually telling you that h is equal to 0 at that point. So the height is 0 and the temperature, T, is 20 degrees. Also that at h equals 1, or a height of 1 kilometer, the temperature has decreased to 10 degrees. And actually, that's actually going to give us enough information to actually determine an appropriate model. Now, what you're also going to do is you're going to graph a function, graph the function that we create in part A, and then we're going to answer the question, what does the slope represent? And then we're also going to figure out the height of the temperature at that specific height of 2.5 kilometers. So let's take a look at the solution of this. Because we're assuming that t is a linear function of h, we can substitute in t and h for y and x in our original linear model. So I know that any linear model will always take the form of f of x equals mx plus b. And what we're doing is, since t is my dependent variable and h is my independent variable, I'm substituting in t for f of x and h for x, and so this becomes my new model. We're given that the temperature, or we already established that the temperature was 20 degrees when the height was 0. That was at the ground temperature. So I know that 20 is equal to, plugging in the 20 and the 0, that 20 equals m times 0 plus b, or that just equals b. So we already we just figured out that the y-intercept of this function is 20. Okay, so now let's use the other piece of information that we're given. That is that at 1 kilometer high, the temperature has dropped 10 degrees. So now I'm going to plug in the temperature is 10 degrees for t, and I'm giving the height of 1, and I'm going to use this equation to solve for m, or the rate of change of the function. And so the slope of the line, therefore, is 10, or negative 10, and so the required linear function that models this situation is t equals negative 10h plus 20. This is a very nice linear model. What I can do from that is I can create a graph that will represent this function. So this is the graph of that function. The slope is negative 10 degrees Celsius per kilometer, and is represented at the rate of change, or it represents the rate of change of the temperature with respect to height. So for every kilometer that you increase in height, you decrease by 10 degrees. So I can look at this model and I can start to predict at specific heights what specific temperatures will be. So we're going to use that, and we're going to establish, well, at the height of 2.5 kilometers, the temperature should be what? So we take the height and we plug it into our function that we figured out, And we can establish that T, which is going to be equal to negative 10 times 2.5 plus 20, gives us a final temperature of 5 degrees Celsius. If there is no physical law or principle to help us formulate a model, we construct something called an empirical model, which is based entirely on collected data. So when we're talking about physical law or principle, we're talking about laws in physics that we have that are already established, like the force of gravity or force calculations or anything that has already been established for us to sort of latch onto and generate our models. The temperature model that we just used was an empirical model because all we had was data that we collected or that was collected for us to fit the model. We seek a curve that fits the data and in that sense, and it captures the basic trends of the data point. Because of this and because of the way data usually works out, we're probably not going to use a linear model too much. We're probably going to use something a little bit more complex or a polynomial. So you've probably heard the word polynomial before. It just means many terms in Greek. A polynomial or a function p is called a polynomial if it takes this form. So p of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and then the little dots in the middle means that there's a lot of stuff that's happening in between, but we don't need to explicitly write it. It is understood that that it's there. N is a non-negative integer, and the numbers a sub 0, a sub 1, a sub 2, a sub n are constants, and they're called coefficients. So they're the coefficients of the polynomial. The domain of any polynomial that we're going to work with is 9 times out of 10 going to have a domain of negative infinity to positive infinity, or all real numbers. And then if the leading coefficient of a sub n does not equal 0, then the degree of the polynomial is n. So for example, if I have the function p of x is 2x to the 6th minus x to the 4th plus 2/5 x to the 3rd plus rad 2, the polynomial is the degree of 6. It's just going to be the leading degree or the leading exponent. The highest value exponent will be the degree of your polynomial. And generally, if you do not have it in standard form, meaning you don't have the exponents going in the right order from greatest to least, then you have to reorganize your function so that it is in standard form and you can accurately describe the degree of that polynomial. Now, over your summer homework, you should have learned how to do some factoring with these, things like synthetic division. Those are actually things we're not going to use too much this year in calculus because we're going to have derivatives and differentiation on our sides to help us break down some of these really funky functions and get the roots out of them. But in terms of modeling, we can start to work with the polynomials that we have. So in terms of, or talking about polynomials, if we think about the linear models that we were just talking about, those can also be considered polynomials. A polynomial of degree 1 is in the form of p of the x equals mx plus b, and it's a linear function. And so basically any linear model will also be considered a polynomial. It's just a polynomial of degree 1. The ones that you're probably more familiar with is a polynomial of degree 2, which is ax squared plus bx plus c, and we also call it a quadratic function. Those are things that you have been working with probably since about 8th grade, and we will use them quite heavily this year. Because of that, if we review what we know about it, the graph of a quadratic function is always going to be a parabola. And it's always a graph of a parabola obtained by shifting the parabola y equals ax squared. The parabola opens upward if a is greater than 0 and downward if it's less than 0 or negative. So if the leading coefficient is positive, then the parabola will open upward. If the leading coefficient is negative, then the parabola will open downward. And here I give you two examples of two different quadratic functions, one with a positive leading coefficient, one with a negative leading coefficient. Diving a little bit deeper, I think you probably saw these in Algebra 2 last year. A polynomial of degree 3 is the form px equals ax cubed plus bx squared plus cx plus d, where a does not equal 0, and it's called a cubic function. I give you 3 graphs below of two different cubic functions. One cubic function, a quartic function, and a quintic function. So graph A is going to be a cubic function. If you notice, it kind of has a nice gentle S-curve to it. These will get more extreme as you start playing around with coefficients. The quartic function, which will actually be a 4th degree polynomial, so quartic. Looks very similar to a parabola, and the quintic function, which is the fifth degree polynomial, also looks like a cubic function. And basically what happens is that once you get past degree 3, polynomial functions alternate between looking like cubic functions and looking like quadratic functions in terms of their graphs. So odd degree functions will look like cubic functions, just more extreme, and even degree functions will look like quadratic functions, just more extreme. So if you notice, the quartic function it kind of looks like a W, but it's still pointing up in both directions, whereas a cubic function or a quintic function, one endpoint is pointing down and the other endpoint is pointing up. Let's take a look at an example and see how we can adequately model this situation. So if I give you a ball is dropped from an upper observation deck of the CN tower, which is 450 meters above the ground, and its height h above the ground is recorded at 1 second intervals in table 2. So I give you the table at time 0. The height of the ball is at 450 meters, and then at t equals 1, it's at 445. But if you notice, this is decreasing by 5, and then this is decreasing by 45. This is negative 4. It's decreasing by 14. So this is not decreasing at a constant rate. So the use of a linear model to fit the data is actually out. The best bet that we have for generating this model is going to be the graphing calculator. And what we'll be able to do with the graphing calculator is you will create a scatter plot. So you're going to make a scatter plot with this data. And you're going to look at the plot of the data. So I have that actually already made for you. So we draw a scatter plot of the data in Figure 9 and observe that the linear model is not appropriate. If you try to draw a linear model through this data, you're not going to hit most of the lines. But what you should notice is that the function does have a nice curve to it. And so what it should suggest is that this model would probably be a quadratic model. And so if you were to use your calculator, you would generate the scatter plot, and instead of creating a linear regression, you would create a quadratic regression. And we're going to have some practice with regression this week. Okay. So it looks as if the data points might lie in a parabola, so we can try a quadratic model instead. Using a graphing calculator computer, we created the scatter plot, and we can obtain the following quadratic model. So this is the model that the calculator gave me, which is 449.36 plus 096 t, should be t, minus 4.9 t squared. We can ignore this ts. That's a typo. And this is a quadratic model, and basically what I can do now is that since I've created this quadratic model, I can use that, and I can predict at what time this ball should hit the ground, or I should try to figure out the roots of the function. So in order to do that, I want to figure out when h equals 0. So I set this equal to 0, and I'm going to solve for t. Okay, so this is the path of the ball. And so if the ball hits the ground when h equals 0, we can solve the quadratic equation. And we're going to use the quadratic formula. Since this is a linear model and it does not have nice values in it, the only thing we can use is the quadratic formula. So when we plug into the quadratic formula, the positive root is at t equals approximately 9.67, so we can predict the ball will hit the ground after 9.7 seconds. Power functions. So these are very simple. They're sort of simplified versions of polynomial functions. A function in the form of f of x is equal to x to the a, where a is a constant, is called a power function, and we consider several cases. So the first one is that a equals n, where n is a positive integer. So for the graphs of f of x equals x to the n for n equals 1, 2, 3, and so on, they're actually just considered to be polynomials with only one term. And we already know the shape of each one of those graphs. So, for example, we know that y equals x is equal to a line through the origin of slope 1, y equals x squared is a parabola, and these are all those functions. So this is y equals x, and these are all power functions. They're essentially polynomial functions with just a single term. Now, if we start to get a little bit more, the general shape of the graph of f of x equals x to the n depends on whether n is even or odd. If n is even, then f of x equals x to the n is an even function and is a graph similar to the parabola. So this is like what I was saying, that once you get past higher degrees of 3 and 4, or 2 and 3, that the graph is going to alternate between being an even function and being an odd function. Odd degrees will mean odd functions. Even degrees will give you even functions. So here's an example. If you notice in Figure 12, however, that as n increases, the graph of y equals x to the n becomes flatter near 0 and steeper as the absolute value of x is greater than or equal to 1. So if x is really small, then x squared is smaller, and if x cubed is even smaller, and so on and so on. So what you should notice is that what it's saying is that from here, between x equals 0 and x equals 1, with higher degrees, you're going to start getting flatter and flatter curves between 0 and 1. And that is because if you start squaring the values or cubing the values or raising to the fourth power, that the values of between 0 and 1 are going to get smaller and smaller as you raise them to higher and higher powers. And it doesn't really matter what the parity of the exponent is, if it's even or odd, it's still going to do the same thing, whereas like if this is x cubed here, and then x to the fifth will actually be a little bit flatter. The second case we have to deal with is that if the exponent is a rational number, or so a is equal to 1 over n, where n is a positive integer. So for example, the function f of x equals x to the 1 over n is really just the nth root, or it's going to be a root function. For n equals 2, it's the square root function, whose domain is 0 to infinity, and whose graph appears to be the upper half of a parabola x equals y squared. For other even values of n, the graphs of y equals the nth root of x is similar to that of y equals the square root of x. So very much similar to the first case of power functions that we were talking about. As you increase in even values, the graph of the function is going to be very similar. It's just going to increase, or it's going to flatten out the curve between 0 and 1 again, but this time instead it would be the y values, as between 0 and 1 on the y-axis, those graphs will start to flatten out. For n equals 3, we have a cube root function, which is going to look a little bit different. And if you recall, the domain that every real number has a cube root, and whose graph is shown in the figure 13b, the graph of y equals the nth root of x for odd is very similar to that of y equals the cube root. So if these functions are going to alternate back and forth between even and odd exponents or even and odd roots, and they're going to alternate back in terms of appearance. So fifth root of x will look very similar to the cubic root of x. Seventh root of x will look very similar to the cubic root of x. What's going to happen is it's the flatness of the curve in between 0 and 1 on the y-axis. The third case that we're going to deal with is when you have a equals negative 1. So if you remember, whenever you have a negative exponent, the way that you make it positive is to take the reciprocal, and that's why these are called reciprocal functions. So for f of x equals x to the negative 1, it's going to turn it into actually 1 over x. And when we start dealing with variables in the denominator of functions, that's when we start getting asymptotes and other kinds of restrictions. So the equation y equals 1 over x, or xy equals 1, is actually just a hyperbola with the coordinate axes as its asymptotes. So this function arises in physics and chemistry in connection with Boyle's law, such that when the temperature of a constant, when the temperature is constant, the volume V of a gas is inversely proportional to the pressure P. So I have the equation for Boyle's law, which is V equals C over P, where C is constant. Thus, the graph of V has a function, or as a function of P, it has the same general shape of the right half of figure 14. So this is actually a reciprocal function. But since we're dealing with real-world situations, you can't have negative volume, so we only actually focus on the right half of this graph. So we use this part of the graph to talk about Boyle's law. You can't have negative volumes. And then the last kind, or one of the last kinds of functions we'll talk about are rational functions. A rational function f is the ratio of two polynomials. So instead of just dealing with, or it's a fraction containing two separate functions, one on the top and one on the bottom. And what we do have to take into consideration is that the domain will be affected now that we're dealing with fractions and we're dealing with variables in the denominator. The domain consists of all the values such that the bottom function, or the q of x, cannot equal 0. A simple example of a rational function is the function 1 over x, the one that we just talked about. The domain is that x can't equal 0. So you'll have asymptotes wherever the x value is going to equal 0. So at x equals 0, or the vertical, or the y-axis, you're gonna have an asymptote. So if we think about another rational function, this one's a little bit more complex. F of x is equal to 2x to the fourth minus x squared plus 1 over x squared minus 4. If you look at this function, if we wanted to state the domain of this function, we would have to factor out the bottom, which would be x minus 2, x plus 2. And so that means that the domain cannot equal positive or negative 2. And that actually corresponds with these two vertical asymptotes here. Now there's also something happening with this part of the curve here. It has to do with a slant asymptote. That's not something that we have to talk about. If you did the summer assignment, there was a little bit of talk of slant asymptotes. Algebraic functions. A function f is called an algebraic function if it can be constructed using algebraic operations, such as addition, subtraction, multiplication, division, and taking roots, starting with polynomials. Any rational function is automatically an algebraic function. Here are two more examples. So I have f of x is the square root of x squared plus 1, where we're combining a root function and a polynomial function. G of x is equal to x to the fourth minus 16x squared over x plus rad x. This is a really long one, plus x minus 2 times the cube root of x plus 1. This is a very complex function. We will probably not do anything with it. But it's just a demonstration of what an algebraic function. So it's constructed using basic algebraic operations. There's subtraction, division, roots, powers, and it's used to create this new function. The graphs of algebraic functions can assume a variety of shapes. So each one of these represents an algebraic function. So the first one being x times x plus 3. If we take a look, you can get these in your notes. The fourth root of x squared minus 25, x to the 2/3 times x minus 2 squared. An example of an algebraic function that occurs in the theory of relativity is the mass of a particle with velocity v. So this is actually a real-world application. This is something that we can construct and hold on to. So the mass of a particle with velocity v, so mass is equal to, as a function of velocity, where it's the initial mass divided by the square root of 1 minus the velocity squared over c squared. And we have this c squared value, which is the speed of light in a vacuum. And we can use this, and we can use this function, and we can determine the mass of a particle in space. Trigonometric functions. In calculus, just as a convention, we're always going to use radian measure, except when we're otherwise indicated. Very rarely are you going to be working with degrees. So for example, when we use the function f of x is equal to sine x, it's understood that sine x means the sine of an angle whose radian measure is x. Thus, the graphs of the sine and cosine functions are shown here. We use the radian benchmarks to create our graphs. We don't use the degree benchmarks. And generally when we create a graph, we're only going to use a period of 0 to 2 pi. You generally only have to graph about 1 or 2 periods. If you notice that for both the sine and cosine functions, the domain is from negative infinity to positive infinity, and the range is actually a closed interval from -1 to 1, and that will change depending on what you do to the amplitude of the function. So for all x values, we have -1 is less than or equal to the sine of x, which is less than or equal to 1, and it's the same for cosine. So -1 is less than or equal to the cosine of x, which is less than or equal to 1. or in terms of absolute values, the sine of x is less than or equal to 1, and the cosine of x is less than or equal to 1. Also, the zeros of the sine function occur at integer multiples of pi. So when sine x equals 0, then x is equal to n pi, where n is an integer. So you should see it in the graph that for the sine curve, you'll have integer multiples of pi. So you'll have pi, you'll have 2 pi, 3 pi. Multiples of pi will get you to the next integer or the next intercept on the graph. An important property of the sine and cosine function is that they are periodic functions and have a period of 2 pi. That means that for any value of x, the sine of x plus 2 pi is going to give you the sine of x. So if you take whatever value and add 2 pi to it, it's going to give you back the same thing. And same thing for the cosine function. This is just a nice way of simplifying things. The tangent function is related to the sine and cosine functions by the equation that we know, which is tan x is equal to sine over cosine. And its graph is shown in figure 19. It is defined whenever cosine x is equal to 0. And that is when x is equal to plus or minus pi over 2 or plus or minus 3 pi over 2. Basically odd multiples of pi over 2. Its range is from negative infinity to positive infinity. And if you notice that the tangent function has a period of pi, the remaining 3 trigonometric functions, the cosecant, secant, and cotangent, are reciprocals of the sine, cosine, and tangent functions. We probably won't use them too much. If we talk about exponential functions, there are functions of the form f of x is equal to a to the x, which is very easily to mix up with power functions, where instead of the variable being in the base, now the variable is in the exponent. The graph. So I have two graphs here. I have the graph of 2 to the x and y equals 1/2 to the x, are shown in figure 20. In both cases, the domain is negative infinity to positive infinity, and the range is going to be 0 to infinity, mostly because we don't want to have negative values, or we won't have negative values when we're raising to an exponent. Exponential functions are useful for modeling many natural phenomena, such as population growth or radioactive decay. These are probably the more reasonable models that we would use. Another one is logarithmic functions. So the logarithmic function, or f of x is the log base a of x, where the base a is a positive constant, are the inverse functions of exponential functions. In figure 21 shows the graph of 4 logarithmic functions with various bases. In each case, the domain is from 0 to infinity, and the range is from negative infinity to positive infinity. And the function increases slowly when x is greater than 1. So you should notice that it increases very rapidly until x equals 1, and then it starts to flatten out and get very slowly. So what we're going to do is we're just going to identify just different types of functions. So if I look at the first one, f of x is equal to 5 to the x. This is going to be an exponential. Because the variable is in the exponent, which is very similar and very easy to mix up with the second one, g of x is equal to x to the 5th. This is a power function. The placement of the x will slightly change, and it can change the entire property of the function. H of x is 1 plus x over 1 minus the square root of x. Since it is a ratio, I can call this a rational function. And the last one, 1 minus t plus 5t to the 4th. This is just a simple polynomial function of degree 4, because 4 is the highest exponent. Let's take a look. And here are the solutions. So f 5 to the x is an exponential function. X to the 5th is a power function. They called it an algebraic function. It could also be considered a rational function. It's two polynomial functions, one on top of the other. It just so happens that the degree is 1 on the top, and it's half for the other one. And then the final one is a polynomial of degree 4. That is it for this video. I know that this was another long one. And we'll do some work with polynomials in class. See you then.